As I mentioned, we are moving from image processing for noise removal, artifact removal, enhancement, filtering, to detection. Detection of regions of interest, ROIs. A region of interest is what you are using for further analysis. And you may extract certain regions that could contribute to further analysis of the image and say that the remaining parts of the image are not of interest. The regions could be tumors, could be calcifications, could be entire part of the breast, for example, or parts of the breast, parts of the lungs, and chest, and so on. Could be landmarks that you could use for registration. So some parts of the image that you want to use further for some other purpose, specific parts, and the other parts are not of interest for that application. You may want them for something else later. In digital image processing without the medical application, this could be called segmentation. But segmentation has other connotations. I'll mention that too. So let's start with this topic now. It's a little lengthy topic. Many applications and illustrations will come up with various techniques. So in computer-aided diagnosis, or CAD, one of the roles of image processing is to detect regions of interest, or ROI, for further application, then perform characterization of those regions. Characterization means extraction of features and measures. And it is expected that those particular regions will help in making that kind of further analysis, be it for diagnosis or some other purpose. So what are these regions in typical medical images? Cells in cervical smear test images for pap smear test analysis to detect cervical cancer. Calcifications in mammograms have shown. Tumors and masses in mammograms have shown. The pectoral muscle in mammogram we will see. The breast outline or skin-air boundary in mammogram, we will see that later. The fibroglandular disc in mammograms, we will see that. Airway tree in lungs, arterial tree in lungs, or the arterial tree in the brain. The arterial tree of the left ventricle in particular, where constricted parts due to plaque development or deposition of something, you may want to detect that in particular after you detect the blood vessels. Segmentation is the process that divides an image into its constituent parts, objects or regions. So all. So there are benches and tables and this and that and people and so on. So you break an image into all of the parts. Now in medical image processing, we may not want all parts. So segmentation is an essential step before description, recognition, or classification. It is not possible to characterize a mammogram by processing the entire mammogram. You can get a histogram, it doesn't say much. Take a spectrum, it doesn't say much because there are so many things in the mammogram. All of those, if you put them together and extract some combined feature, that won't help you. So you need to break the image into some parts, not all parts. So two major approaches. One is based on discontinuity. When there is change, there is this sort of yellow background, there is blue, or this is sharp, this is smooth, something is changing. So I say, okay, there is a boundary. That's a different object. Similarity. Homogeneous parts are detected, and by putting together, this pixel is similar to that and that and that, so I put them all together. And I come here, this is different, so this pixel is different, but these are all similar, so group them together. So like that, you can use these two properties together or separately and say, when you say similarity, yes, when you keep growing, there will be some boundary. That is dissimilarity or discontinuity, then you stop. So both of them are used. So there are applications where entire images need to be analyzed for global changes in patterns. You want to compare the whole thing. But images have multi-component regions, and analysis may commence with the detection of single units in the pattern of interest. So several such units may be present in the image, and you may need to analyze them each separately and also together, like calcifications. I showed an image with several calcifications. You want to detect each one of them find the density, shape, and then find the distances between them, find the shape of that cluster, how many are there per centimeter square, and so on. What is the spatial distribution? Are they in a straight line? So for that you have to detect each one and detect all of them, calcifications, and then put them in a map and study that distribution. So then you can say it is multi-component analysis. It's not just one region. So some basic techniques, thresholding we have seen. If a value of Mn is less than some threshold, 0, otherwise 255 or 1 or some other number. So this is the collagen fiber in cross section I showed earlier. If you threshold it, you get that. The black areas are the collagen fibers. The white areas are just background tissue. And then we can detect each one of them and get the diameter or size. That's what we were interested in. We wanted to get the diameter distribution of collagen fibers in such images. If you take a histogram, I showed this earlier, of the original image, because of noise there is so much variation. After filtering, you get a good bimodal histogram. When you have an object versus background, you expect the histogram to be bimodal. One mode for the object and one mode for the background. In this case, the background is brighter. Note that each of these modes has a certain width. That means there is variation within the object and variation within the background. That's the variation for the object. That's the variation for the background. There is no optimal threshold here. If they were completely separated, you would expect two separate distributions. And then any threshold here can separate them. If your imaging technique is perfect and ideal, or your feature extraction, this could be the feature you have computed for normal and cancer. If you can compute such features, you hit the jackpot. Any threshold will work and give you 100% accuracy. But that doesn't happen. You get this, where this distribution is continuing and that distribution started somewhere there. There is so much overlap. Still, optimal threshold will say, find something in this valley between the peaks. And if you can find a valley, then we can minimize the artifacts of misclassification of background as object or object as background. So that is basic thresholding. I'll discuss other thresholding methods later. There are a few masks you could use to detect points and lines. If you expect single points or point-like objects that are isolated against some background, then you can use the derivative like this. The central pixel minus the sum of the surrounding or average of the surrounding. If you divide this by 8, you get 1 here and minus 1 over 8 there. So this is useful in identifying particles. You can also use it to filter such noise, if that is noise. Or you may say, I will detect such things. So you want to extract them or suppress them. Straight lines may be detected by using templates. This is the template for a straight line. And that's the background within a 3x3 mask. Why 3x3? That's just convenient, that's all. You want 5x5, go ahead and do the same thing with 5x5, 7x7. So diagonal line, vertical line, diagonal that way. So this is a derivative. The sum of all the coefficients is equal to 0. So you are doing a kind of template matching. My template is this. This is what I want to detect, but I want to compare it with the background, and there must be a good difference between that object and the background. So it's also a derivative. So you run this over the image, and wherever there is a big response, you say that pattern has been found there and mark it. Or this pattern. So you have to run multiple templates. For edge detection, there are a few convolution mask operators. We will start with basic techniques and then look at advanced methods. An edge is characterized by a large change from here to there, or from here to the object, to this character. In a particular direction, here it is in the vertical direction, here it is in the horizontal direction. So it is directional. So gradients or derivative measures of the gradients or derivatives give you a measure of the rate of change, and they form the basis for edge detection. In 2 dimensions, gradients will have direction. So you can take the derivative in the y direction or x direction, and you may look forward or backward, or to the left or right, or this is right, left, top, bottom. So how do you want to define that? So you can call this yf prime yb, fmn minus fm minus 1 previous row, if you are using matrix notation. So this is where again you have to consider, is this horizontal or vertical? If it is matrix notation, it's the previous row, so I'm looking that way. If it is array notation, m minus 1 refers, the first index refers to the x-axis. So n is this, m minus 1 is that. So that is horizontal. So whether that is horizontal or vertical depends on whether you are looking at it as a matrix or as an array in the first quadrant. When you combine them, it doesn't matter. So that is one. And in the y direction forward, x direction forward, that is m plus 1, you're looking at the next row or the next pixel in the same, along the same direction in the x-axis. So forward, backward. Now you combine them and you can get a better result because you're averaging forward and backward, 2 differences. Differentiation increases noise. We saw that earlier. So to suppress noise, you take the average of 2 derivatives, and it could be forward and backward, top and bottom. So averaging the forward and backward derivatives, you get half of m plus 1 n minus m minus 1 n. So now the central pixel is gone. You're comparing the one pixel this side with the pixel that side, jumping over the center pixel. And the same in the other direction. That forms the basis of the Privet operators. You're comparing this, that. And now instead of taking the horizontal derivative is this only. But further averaging, you say, well, these are neighbors, so I'll do the same operation there, top and bottom, and put them all together. If you want, you can put 1 over 3. Because there are 3 of those. The sum of those is 0. So it's a derivative. Vertical, again the same idea. Combining 2 of the derivatives forward and backward, you only get this. But now you say, I'll take the one before and after in that direction, make a nice 3 by 3 mask. And they're known as Privet operators. When I show this, or I show this often to my students, when we discuss projects, some of my students say, oh, this is very difficult. I say, yeah, all easy things have been done before. Only difficult things are left for us to do next. Even more difficult things for you now. Privet got his name for that. To us now it looks, oh, it's so simple. But at that time, nobody had done that. So you combine that, take the x derivative and y derivative because they are in orthogonal directions. You make a complex quantity, gx plus jgy. The f is forward, b backward, whichever you want. And magnitude is the square root of the sum of the squares. The angle is tan inverse or arctangent of the ratio of the y gradient to the x gradient. Okay? Now you can also get this, you get this gradient using the convolution operator. F is convolved with the gx mask that I showed earlier, and this is happening more often now. You should have poured some tea into that. This is obtained by convolving with the other mask. So these are convolution mask operators, and you are getting gradients. Sobel came up with a different idea. Said, well, In the privet masks, those three operators are given the same weight for the current one and the one above and one below. Why not take a weighted average? Give more weight to the current horizontal line to -2, that is, it was -1, double it, and let the others get only half that weight. Still, the total sum of the weights is 0. So that is the horizontal, vertical. Again, which is horizontal, vertical depends on your interpretation of this as matrix or array in the first quadrant. So that again is a simple modification of privet, and it's called Sobel, and we call it Sobel, and he gets the credit for that. Simple thing, but it's been done. If you want this gradient at different angles, rotate. So that forms the reference line, or this, +1 here, -1 there, or -1 here, +1 there, depending on the direction, if that direction is important to you. If you want to go only 0 to 180, or you want to go 0 to 360. You have to consider those. And the same for the Sobel, you can rotate that. Okay, I think I already mentioned that. Now there is another interesting mask that was developed in the 70s with a specific consideration of storage requirements. When I was a grad student, I said at IISc Bangalore there was one computer in a big building, and that was it. Not only for the students of IISc but also for ISRO. So whenever ISRO satellite passed and there would be data coming, we all had to sit and wait, go to the coffee shop, and our programs would be pushed out. So at that time, that one machine had some limited memory. I don't know how much it was, a few kilobytes perhaps. So you couldn't go and declare a thousand array in your program. It was impossible. And you couldn't have two of them. In image processing, you want at least 100 by 100, but you couldn't have two of them, one for input, one for output. So Robert said, well, we can do in situ processing, that is in the same array. You can put the output value at that pixel as long as you don't use it again. You cannot use the processed value further in processing the neighbors. So the derivatives were defined as -1, 1, 0, -1, 1 that way. This is the reference. And once you finish processing this, you put the result in the same location. When you go to the next pixel, that pixel is not used. Or when you go to the next row. So when you go in the raster scanning order, row by row, column by column, then the process pixel doesn't come in again in the analysis. So you could write the result in the same array. That was the specific idea and requirement. Do you want to do that in your images? I don't know. It depends on the requirements. But these are neither horizontal nor vertical derivatives. They are cross-shaped. Right? You cannot get the gradient angle and so on. It's some gradient. You could take the absolute value of those two and combine them, and it's a forward-looking operator, and the result may be written in the same array as the input image. It may still be useful if you have limited array and limited memory and you have a huge image from pathology slide scanning or remote sensing or something, but I don't think that is an issue anymore. So here are some examples. The shapes, one of the shapes test images. This is the gradient magnitude. Even the gradient magnitude could have a large dynamic range, more than the dynamic range of the input. Here I'm displaying 0 to 400 out of 0 to 765. Mapped to 0 to 255 for the display. So when you process an image, the result could have, as I said, negative values or positive values, fine, but a larger dynamic range than the input. Then you have to compress it to 0 to 255 for display, or select a suitable range. So here we have the horizontal derivative, vertical derivative, and 135. No, this is 45, this is 135 degrees. So you can see that this is negative, but here this is negative. And let's see where. The horizontal edges are wiped out, but here horizontal edges are highlighted. And the opposite happens. When you combine them, you get all edges. For the clock test image, take the horizontal derivative. Anything that is horizontal is wiped out. But what is vertical is highlighted. I didn't plan it this way. We didn't plan to take the picture at 2 o'clock, and how many minutes is that? 22 minutes. But this is at that angle of 135 degrees. So the 135 degree derivative wiped that out. And a few pictures like that. I'll skip those. Now, we saw the Laplacian earlier. The Laplacian is the second order derivative, and it helps in detecting edges, but it is sensitive to noise. The Laplacian of Gaussian combines the Laplacian operator with a Gaussian. A Gaussian is this bell-shaped function, you know, and that if you apply only the Gaussian, it's a low-pass filter, smoothing. By combining the two, we have some advantages. The Laplacian is a second-order gradient operator, but it gives you double-edged outputs. We said that's a problem in the sense it creates some artifact, but you can use that to advantage, as you will see with the Laplacian of Gaussian. It is omnidirectional, so it detects edges at all angles. It is not possible to get the angle of an edge because you took just the square root of the square of the two components. It is sensitive to noise. There is no averaging included in the operator. And the gain increases quadratically with frequency. And you cannot use it directly in edge detection because of these issues. Here is an illustration. The profile of an edge that is blurred, but like a trapezoid, just convenience, it's just hand-drawn example. If you take the derivative, 0, and it goes there, and this is positive for that range, and then the derivative is 0, and then this is negative slope, you get that. Take another derivative, you get impulses here. So I showed this earlier as causing this ringing or black and white bands in the output here at an edge. The edge is here, but you have positive, negative, negative, positive output. But there is an interesting property here, positive, negative. So at this location, there is a zero crossing. The output is crossing the zero axis between two values. And then here again, there is a zero crossing. So the zero crossing gives an idea as to where the edge is, more than the value of this derivative. Of course, when there is a broad edge like that, where is the edge? It's somewhere in between, and zero crossing will help even when these values are very small. Even if these, I have drawn an impulse, it's of some value, but even if it is very small because the gradient is poor, this is positive, this is negative, and that gives you a clue as to where there is an edge, regardless of the magnitude. So that is taken to advantage when using the Laplacian of Gaussian. The double-edged output of the Laplacian shows that there is a zero crossing between the positive and negative outputs. Even when the edge in the original image is blurred, that is, the gradient has small magnitude. And that is useful in the development of robust edge detectors. So here we are viewing edges as regions of interest. They can be combined to detect an object later if you wish. Noise sensitivity is another issue. So include a smoothing operator. What is a smoothing operator? A 2D Gaussian function with the variance of the Gaussian controlling the blurring. The width of the Gaussian is controlled by its variance. The mean is 0. It doesn't matter. Mean is not of interest, let's say, not 0. The width is controlled by the variance, which is a parameter now. So there is a parametric control of smoothing combined with the Laplacian. So this is known as the Laplacian of Gaussian, or LOG, or log operator. Not the logarithm, but Laplacian of Gaussian. So consider this Gaussian. Gxy is exponential x squared plus y squared divided by 2 sigma squared. And the mean is taken out. You don't need that. So take the derivatives, you get this. I won't read that. These are the second order partial derivatives. Combine them and change to polar coordinates. R is square root of x squared plus y squared. You get this expression. So that is the Laplacian of Gaussian operator, which is characterized. R is distance, so it's not a parameter. Sigma is the parameter that controls smoothing or noise control. Okay? So it is isotropic. It's a function of R, which is square root of x squared plus y squared. So there is no direction. It has positive and negative values, and due to its shape, it is referred to as the Mexican hat or sombrero. This here. This is just the Gaussian. Let me see. Gaussian is this part. This is the Laplacian of Gaussian. So there is the positive part and then the negative part. There is a circle that is there. E and F show the Fourier spectra. This is the Gaussian. This is the Laplacian of Gaussian, which is a bandpass filter. The gain around DC is 0. And it is isotropic. And after that, the gain is 0. So that is the Laplacian of Gaussian. This is, D is the point spread function. This is the Gaussian. And that's as a picture. Positive, negative. And outside that, 0. An approximation to the log operator is provided by taking the difference between two Gaussians, and that's known as the DOG, or if you want to call it dog, you could, but that's a difference of Gaussian operators. If you take a section, the Laplacian of Gaussian looks like this: positive, negative, and negative here. That is just the Gaussian, the dashed line. And here, the lower one, the upper one has sigma equal to 4 pixels, the lower has sigma equal to 2 pixels, narrower, less smoothing. This has more smoothing. But the structure is the same. Main positive lobe and 2 negative side lobes in profile. But if you go all the way around, it's isotropic. So that ring is there all the way around of negative values. If you take the profiles of the Fourier transform or the frequency response in magnitude, you get this band pass filter. 0 frequency here, and it's a high pass filter, and then it's a low pass filter. But it's the same all the way around. This is of the first one with sigma equal to 4 pixels, sigma equal to 2 pixels. This is less blurring. It's passing more high frequency, broader pass band. This has a narrower pass band. Both are band pass filters. A Gaussian only will have that dashed line as the response, which is also a Gaussian. Low pass filter. So the Gaussian is low pass. The Laplacian of Gaussian is band pass. So the shape's test image, and this is the Laplacian of Gaussian with sigma equal to 1 pixel. And these are locations of the zero crossings. And this is if you use sigma equal to 2 pixels. So you don't use the output of the Laplacian of Gaussian directly as to view. You could if you want, but perhaps the Laplacian itself is good to view, but to detect zero crossings and mark those as edges, you use the Laplacian of Gaussian, find where there is a zero crossing, that is adjacent values are going positive and negative or negative to positive. There's a sign change, that's all. If adjacent pixels have a change in sign, mark it. That's what I did, and that's what you got. Now this is a multi-scale operator or scale-dependent operator with the factor sigma, the Gaussian width. So that contributes to, you can say, smoothing or blurring. But that also helps in adapting to objects of different size. So it is scale dependent. It's a scaling parameter. So these edges can help in multi-scale analysis as to how these edges vary and what are the scales of the object and where, at which point will some of these objects disappear. And I'll show more examples of that later on. But as you can see here, there is a variation in the positions of the zero crossings depending on sigma being 1 pixel or 2 pixels. So again, that's the original Laplacian of Gaussian, positions of zero crossings marked as a binary image. This is perhaps a better example. The clock image, Laplacian of Gaussian. Now Laplacian of Gaussian has both positive and negative values, so you need to display it with scaling, so that's why it looks dull. And its dynamic range is compressed to 0 to 255. But if I look for sign changes and mark all pixels where there is a change of sign with sigma equal to 1, I get this, which is very noisy. This is a noisy image. If you detect all zero crossings in the Laplacian of Gaussian without smoothing, noise will cause a lot of false detections of what could be edges or not. So all of these pop up. If I put sigma equal to 2, all of these are gone. So fine details, which could be noise or something that I'm not interested in, can be disregarded or smoothed out by using a larger sigma, and I'm getting only significant zero crossings, significant edges. If I use sigma equal to 4 and so on, then it will change further. But I think this is good. I can see the minute hand. I can't see all the numbers, 6 and 5 and so on, but their boundaries have been marked. The original image is quite blurry, it's hard to detect, and it's very poor resolution, 100 by 100 or something like that, pixels. So if you have a better resolution image, you'll see more of them later on. You can get better results. Scale dependent analysis. So that facilitates multi-scale. What is scale? Sigma. Different values of sigma, you generate different zero crossing maps like this, and you create a stack of them. Sigma equal to 1, 2, 3, 4. They're all images, stack them up, and analyze where the zero crossings are. There's a zero crossing map created. And I'll talk about that later on. So here also, there's a lot of noise here in the video image. Sigma equal to 2 gives a lot of noise. Sigma equal to 4, it's creating these false contours, but there are fewer zero crossings here than there, and these edges are staying. The strong edges will remain at multiple scales. That's one of the foundations of multi-scale analysis. The same here. All this noise disappears with sigma going 1, 2, 3, 4. You see all of these small things? They show up here, but they don't show up there. Some of them are here, the large ones, but the small ones go away. I'll skip that. So, scale space methods for multi-scale edge detection is a topic that's been around for perhaps 50 years now. Marr and Hildreth came up with this idea that physical phenomena may be detected simultaneously over several channels. By physical phenomena, they meant real edges, real strong edges, not false edges. Or we can relate what they called physical phenomena as real edges due to a physical thing like that myocyte or the clock and so on. Tuned to different spatial sizes or scale, the sigma parameter, with an approach known as spatial coincidence. An intensity change that is due to a single physical phenomenon is indicated by zero-crossing segments present in independent channels over a certain range of scales, having the same position and orientation in each channel. That's what they said. So a single physical phenomenon, you can interpret it as a single real object, not noise. There are zero-crossing segments. They could be broken due to noise or some artifacts in independent channel. Channel means different scales, and over a certain range of scales. Beyond that and before that, they could be not present. Noise, after some level, will go away. As you saw, small things disappear. Channel implies here, if you refer to a book by Marr on vision, and also Levine has a book on, what's it called? Machine and human vision or something like that. Biological and machine vision or something like that. A book by Marr is vision and Levine is vision in machine and something else. In my book I have the references. They talk about the human visual system as a bandpass filter having multiple channels, multiple filters at multiple scales. Are they Laplacian or Gaussian? Are they Gabor filters, which we'll talk about later on? There is some discussion about that. Some say they are Gabor filter-like operators. Some say they are like Laplacian or Gaussian bandpass filters. Essentially, they're all bandpass filters. Let's take it that way. Different bandpass filters at different bands and possibly different directions, which then become Gabor filters. So when they say channels, they are channels of visual perception or perception, visual perception, all right, in a machine or in a biological system. So when they go to from the retina at the back, there is some processing, neural processing, even before the signal goes to the brain, to the visual cortex, there is some analysis. So what goes to the visual cortex is already a processed neural signal. So this analysis is possibly done right behind the retina in some kind of a network. And what is sent to the visual cortex is some information about the picture, not the picture itself. So the use of techniques based on zero crossing generated from different filters of different scales could be more effective than the conventional single scale methods for edge detection, such as Privet and Sobel and so on, or even the Laplacian. One of my postdoc fellows, Jiqiang Liu, he worked on this. He had worked on this earlier too. Zero crossings and scale space. So you detect zero crossings at every scale. I showed you, I'll go back. Not that. Where did I have 1, 2, 3, 4 here? Sigma equal to 1, 2, 3, 4. So you make a stack, put this on one on top of another, and look through them and see how the zero crossings merge and end, begin and end, and merge in between. And that gives you an indication. That is the scale space. The scale is sigma, this is the space, and zero crossings are those positions marked, the xy coordinates of those positions. So the scale space is generated using this nabla square G. This is Laplacian of Gaussian. Laplacian, Gaussian. xy, sigma is the parameter of the Gaussian scale. Sigma greater than 0, 1, 2, 3, 4, whatever you want, 1, 2, 4, 8. It's up to you how you want to sample the scale range. Wittgen came up with this idea of scale space called psi xy sigma of an image fxy, set of all zero crossings, xy sigma such that this zeta xy sigma is 0 and the Laplacian is not 0, scale is greater than 0, and that is the output of the Laplacian of Gaussian. So that is a set of these points I was talking about. This is just a notation for that. As the scale sigma varies from 0 to infinity, that xy sigma forms continuous surfaces. And when you stack those images I mentioned, there is some sort of a surface formed by them. If you do the same in 1D, you get these lines where zero crossings start and merge and disappear. So here in 2D, you get a 3D stack, and in that there are these surfaces of these zero crossing locations. So Liu, my postdoc fellow, suggested the discrete scale space approach to construct. Can we do something about that? Or? It's getting worse. We changed it yesterday, right? So something is happening. Should we turn one of these fans to that, and I'll sweat and that can stay on? So there's the idea of a stability map. Which zero crossings are significant and which are not? There are edges and false edges created by noise, and some are some minor details we're not interested in. So how do we find what are the stable items of information that are important? So a measure of pattern boundary persistence over a range of scale in this 3D stack. What is strong and persistent and stable? So a set of zero crossing maps is generated as we saw earlier, and n is some number, 8 values of sigma I. So instead of directly matching all zero crossing locations at a point, Liu said use this criterion C of sigma I, x prime, y prime, such that there is a neighborhood. X prime is a neighborhood around x controlled by this lambda sigma I. Sigma is the scale, lambda is some scale factor, and the same for y. So x prime, y prime are the actual locations of zero crossings. Xy is the pixel where the filters are being applied, and lambda is a constant, and we just left it at 1. It could be some other number. So you're using a neighborhood, and you're analyzing the zero crossings. And there is a function SIXY equal to kappa if this psi xy sigma I is within this C sigma I. So this is a kind of a strength of the edge, a strength of stability of the zero crossing map. Then there are multiple ones of those, and you combine them and create another zero crossing stability map. So these are over scales. So there's a neighborhood used at a certain plane for each of the scales, and then you combine over the n scales you have used. So that is a measure of boundary stability through the filter scales. S being a measure of strength, a number of points having zero crossing. So using the spatial coincidence assumption or theory, a true boundary should be high in contrast and have a relatively large value of this function at those locations. There should be no other edges within a given neighborhood. You can't have only edges. There should be an edge, and then there should be some gap, and then there should be another object. So if in a neighborhood of this function, non-zero stability map values exist only along the orientation of a local segment of the stability map that crosses xy, then that function may be considered to signify a stable edge. So this is all the argument. Let me see when the picture comes up. I'll skip some of these minor details. The function took into account the distance between zero crossing points. There was an additional point regarding those distances. As I said, you don't want to have strong edges that are too close. So I'll skip all of those minor details and come to the illustration. This is a scanning electron microscopy image of a ligament sample showing collagen fibers lengthwise. So there are collagen fibers of different thickness, and there are some gaps in between. And these are they're all zero crossing locations, 1, 4, and 8. And this is the stability map, combining all of them. Now the stability map has values, and you have to analyze those values to find what are the real edges and which points are not corresponding to real edges. This shows multi-scale analysis. Regions or objects of different size, fine edges, all edges, edges of thick objects like that is shown here. Those edges are there, but they are hard to find because there are so many other things. And here with 8 pixels, 1, 4, and 8, that is actually the gap here. But that's an edge. That's a strong edge. It's not an object. You have to analyze later what is inside here. Is it the object or is it the background? That's further analysis. But edges are detected, and the stability map combines all of these. How many ever you have? I'm showing only 3. We used 8. Okay? There is a continuation of this in another chapter on directional analysis, or analysis of directional patterns, where we have taken this and analyzed this information to find the orientation of every fiber. So this is not the end of the story. This is simply to illustrate edge detection, or what could be used for edge detection. We did not mark the edges here. I'm showing only Laplacian of Gaussian and how to use the Laplacian of Gaussian. Do you use this? No. Do you use that? Maybe. Do you use this? Perhaps not. But they're all important. So how do you combine them? This is one way. Use this and perform some selection of points that you believe are true edge points and mark them. And what you do next is again up to you. You detect the edges, and then what? Which parts are collagen fibers, how thick they are, what is their orientation. That comes later. Okay? Canny's method is a popular method. You have that in MATLAB and many other programs. I won't go into all the details, but the general idea is that Canny said there are 3 criteria for good edge detection: multidirectional derivatives, multi-scale analysis, and optimization procedures. Multidirectional derivatives. If you use partial derivatives of only x and y, then you only have 2. But if you use Gabor filters, as we will see later on, they're not derivatives, but you are getting directional energy in different angle bands. You can also formulate derivatives at other angles, but if you use small masks, the angles are limited. With 3 by 3, you only have horizontal, vertical, and diagonal, that's all. The criteria relate to low probabilities of false detection and missing real edges, represented in the form of a signal to noise ratio. Signal means real edge, noise means false edge. Good localization represented by the RMS distance, root mean square, distance of the detected edge from the true edge. So he said the detected edge must be as close to the real edge as possible. The production of a single output for a single edge represented by the distance between the adjacent maxima. So you don't want double edge output. So those were the criteria and the optimization procedure and so on. The basic filter is the first derivative of a Gaussian. Gaussian has a parameter, so we can use multiscale with the sigma of the Gaussian. Multiscale analysis and directional filters were incorporated to facilitate efficient detection of edges at all orientations and scales with adaptive thresholding and hysteresis. I won't go into the details. It evaluates a directional derivative across each edge and avoids derivatives at other angles that would not contribute to edge detection and suppress the effect of noise. I'll show some examples of Canny's method much later. Let's look at the Fourier transform also. Can we use the Fourier transform? Yes, to some extent we can use high-pass filters, take the output, and then try to threshold. But then it may be a bit difficult and you're adding computation. The other methods we have discussed may be more efficient. High-pass filters may be applied in the Fourier domain to extract edges, we have seen that. The inclusion of all of the high-frequency components could lead to noisy results. So do we need all of the high frequency? No. So then you want to cut the high frequency components. Towards the end of the frequency range, you will have noise. So high pass will take all of that. So that then you say, okay, let me do a band pass. So then you are doing a high pass and low pass coming down, which is what we have seen in the Laplacian of Gaussian. It's a band pass. So it says, well, don't do high pass, do band pass, which is like a Laplacian of Gaussian. So edges are often weak or blurred. Enhancement of the corresponding frequency components would be desirable. What is the band of frequencies where your edges lie? Somewhere in the middle. Not low frequency, not high frequency. So boost the middle. So all of these arguments lead us to the Laplacian of Gaussian filter, which you may implement either in the space domain or in the frequency domain as per your convenience of programming and implementation. Okay? So the Fourier domain implementation is simply a matter of interpretation and convenience. And the Laplacian of Gaussian could be seen in both the space domain and the frequency domain, and how you want to implement is up to you. It will be good to analyze the filter and the results in both domains, so we get a better understanding. Okay? Any questions about what we have talked so far? No? Clear? Okay. So now we have detected these edges. They may not be lines like this, beautiful straight lines or curved lines. You may get a few pixels here and a few other pixels, and some pieces are missing. There could be some artifacts, some other dots here and there. So essentially you get a bunch of dots, and they need to be processed further. So results of most methods for edge detection are discontinuous. They are points marking zero crossings or some property. They need to be processed further to link disjoint segments and obtain complete representation of the boundaries of the ROIs, all boundaries of whatever objects are present in the image. There are two properties that are used to perform this kind of edge linking. One is the strength of the gradient. A point x prime, y prime in the neighborhood of x, y is similar in gradient magnitude if their gradient magnitude difference is small. That is only magnitude. Gxy is the gradient at xy or x prime, y prime. T is some threshold. That is similar gradient. And then angle. The angle should also be similar of the gradient. And for that you need to go back to the gradient. The Laplacian of Gaussian zero crossing map won't give you that. You have to go back to the Prewitt and Sobel operators or some other operator to get the gradient magnitude and direction. So if the angles are similar, alpha xy minus alpha x prime y prime is less than some angle A, that is, they have similar direction, then you say, well, these two pixels belong to the same edge, and connect them. So small neighborhoods, 3 by 3, 5 by 5, may be used to check for pixels that are spatially close by, may not be connected, and say, well, these two should be connected. And then you may fill the line in between. So further processing steps may include linking of edge segments separated by small breaks. So if there is a gap in between two that are, you mark these two as belonging to the same edge, but there is a gap in between, you say, I'll fill it. So small breaks may be connected, and isolated short segments may be thrown out. So that is edge detection and edge analysis. Quite often, edge detection and analysis will give you broken edges, and this edge linking may be a bit of a challenge. You may not be able to achieve good results by connecting these pieces. It's a bunch of dots, and you connect this, so you throw that out. The final result, it may be hard to say this is a tumor, this is a calcification, this is something. Whereas segmentation by region growing perhaps will give you connected pixels and possibly a closed region, maybe even a compact region. Compact meaning no holes inside. So let's look at region growing now. Region growing is typically defined as dividing an image into regions that could correspond to structural units, objects of interest, regions of interest, and so on. There are some conditions that may not apply to all applications. I'll explain that now. There are a few main categories. One is thresholding. We saw that earlier with the collagen cross-section image. Boundary-based methods, we will see that later. Region-based methods and hybrid techniques that combine boundary and region. Thresholding typically doesn't give you the best result. Thresholding methods is based upon the assumption that all pixels whose values lie within a certain range belong to the same class, but we saw it has serious limitations. Boundary-based techniques. Usually pixel values change rapidly at the boundaries between regions. This object and this boundary, this object and this boundary, this object and its boundary here, separating this from that. So you want to detect the boundary. So you start by detecting intensity discontinuities, that is derivatives, using a gradient operation. High values provide candidate pixels for region boundaries, like these. And then you say, I'll connect these and say that is one region, this is one, and that is another. The problem again is some of these boundaries may be broken, then you have to fill the boundaries and make sure that they give you a closed region. Region-based methods. There is the region split and merge, splitting and merging techniques. And then there is region growing. Split and merge says subdivide the given image into a set of arbitrary disjoint regions. Just break into quarters and take each quarter and break further and keep breaking further. Do the first partition and check each of the quarters and see if they meet some condition of having similar pixel values, such as variance. Compute the variance of a quarter of the image. And if the variance is less than some threshold, you say, well, all of that is one region. If the variance is too much, then you break that further into quarters and check the variance of each of those sub-regions. And keep dividing until each region has a variance that is less than some threshold. And then it is possible that some adjacent regions have similar properties, so you have to merge them back. And then you get regions of different shape and size. Otherwise, you just get these squares. So when you merge adjacent regions that have similar properties, then you get better approximations of real regions. So split and merge. First is splitting. Check the property of belonging to one region, one object, typically variance, standard deviation, coefficient of variation, some property. If there is too much variation, subdivide that further, typically into quarters, not arbitrary shapes, and then check each of them. When each region is uniform according to your criterion, say I'm not going to split that any further, and check the other regions. And check for later on, after all the splitting is finished, do merging. Check adjacent regions. If their properties are similar using some other criterion, merge and connect them. And keep doing that until you cannot merge anymore. Region growing is different. You start with a pixel and say, I'll keep on accumulating neighboring pixels that are similar and spatially connected. And the region can grow into any size and shape, as we saw for adaptive neighborhood image processing. When you hit the boundary, then you say, okay, this region is done. Go to other pixels that don't belong to a region yet, and do region growing again. Now these regions are non-overlapping. So the image is broken into non-overlapping pieces of any shape and size. Optimal thresholding is required when, as we saw earlier, these probability density functions or histograms of the objects overlap. You have the gray level of one region or one object, let's say, the collagen fibers, and the background, and they merge here. So the total histogram looks like that. So where do you put your threshold? You want to optimize that. There is an error there. There will be misclassification. So depending upon your optimization criteria, you will get different thresholds. There are many such thresholding algorithms. So a basic one. So there are, let's say, two objects with probabilities P1x and P2x. X is gray level. The PDF of the image Px is capital P1, the probability of occurrence of the object P1x, plus P2, the probability of occurrence of the background, let's say, times P2x. So that is one of them. This is P1, that is P2. Which is background, which is object, depends on the how you take the image, brighter or darker. One of them is the object, the other is the background. And assume that each one is a Gaussian. Then you have these Gaussian x minus mu1 over 2 sigma 1 square, that exponential, some normalization factor, that is one PDF. This is the other PDF weighted with the probability of their occurrence. The capital P1, P2 says how much in general of the image is occupied by the object and how much is background. In general, 40% object, 60% background, or something like that. So these two PDFs are weighted by that. And this is the mean of one of them, maybe there. This is the mean of the other one, which is there. And let mu1 be less than mu2, one of them. Suppose that dark regions correspond to background, bright regions to objects of interest. The opposite of what we saw in the case of the collagen fiber cross-section. All pixels below a threshold T belong to the background, above T belong to the object of interest. Could be the other way around, it doesn't matter. The probability of erroneous classification. What is the error if you use T as the threshold? Capital P1, the first category, from T to infinity, P1x dx. So everything from the threshold onwards of that probability, if you classify as the object, that's the error. And this is the error minus infinity t of p2x, the other one. That's the error of calling that as your object. So the threshold that you put there divides the histogram of the image into two parts, but there is an error because the two PDFs overlap. So to find the optimal threshold, you differentiate PET with respect to t and equate the result to 0, which leads to this condition. And then you solve. You have a quadratic equation. You have to solve for these parameters A, B, C, using these, including these variances of the two categories and their means. I won't go into the detail. So if the variances are the same, then a single threshold may be used. T equal to mu1 plus mu2 over 2, and this. If the two probabilities are equal, then this goes away. And the threshold is just mu1 over mu2 plus 2. That is, the threshold is simply the average of the two means. If the two probabilities are equal. So you just take the mean of these and then take the middle of them. That is one technique with these assumptions. That's not the best, but that's one way of optimization. Thresholding using boundary characteristics is another technique, which says sometimes the number of pixels occupied by the objects of interest could be very small compared to the total number of pixels in the image. There's a big background and a few small objects that correspond to your object of interest, and the number of pixels of the object of interest, a number of regions, or maybe one region, could be very small. Then this histogram will not look like that. It'll look like maybe something like this, and then like that. This is the object of interest. So when you have a small number of counts for the object and a huge number of counts for the background, finding this optimal threshold becomes a problem. Where do you cut? So then the boundary characteristics are important in the sense around each object region there is a boundary. Suppose these are the objects of interest. Very few pixels compared to the whole image. But there are these boundary pixels. And there could be some other objects, some other false boundaries. So it says find the boundaries and use only those boundary pixels and then classify them, or use them in finding the objects. So how do you do that? The number of pixels covered by the objects of interest to be segmented from an image is a small fraction of the total number of pixels in the image. The gray level of histogram will be almost unimodal like that. Histogram may be made closer, not really close, but closer to bimodal if only the pixels on or near boundaries of object regions are considered. So if I say if this is one of these objects, I'll say I'll take a number of pixels outside and inside. So there are a few pixels inside the object and a few of the outside, meaning background. So take a bunch of object pixels and a bunch of background pixels of almost equal number and make their histogram. The background, these boundary pixels, BXY, could be further categorized Bxy is 0 if a gradient measure is less than threshold. It is some value L plus, like 1, plus 1. If the gradient is greater than the threshold and the second gradient is greater than 0. It is some negative value, minus 1, if the gradient is greater than the threshold but the second derivative is negative. So leading and trailing edges, or positive and negative changes. So if you want, you can have three categories, not just inside the object and outside, but outside, not the background where there is no gradient, and on the leading edge and on the other edge. Nabla square is the Laplacian, the other is the grade. This is the gradient. So these are three levels in the output. So the pixels that are not on an edge are set to 0. The pixels on the darker side are set to L plus. Pixels on the lighter sets are set to L minus. So this can be used not only to detect objects and edges, but also identify the leading and trailing edges of objects with reference to the scanning direction. So this, will it give you a bimodal histogram? We have tried that. It doesn't exactly give you a bimodal histogram like this. It doesn't go that way, but it is better than the original. And by using three values, things may be complicated a little bit more. It may not be necessary in most applications, so it is enough if you mark as object and background. So region-oriented segmentation of images. So this is the general theory of how to break an image into parts. Not all of these conditions are applicable in all applications. In medical images, we don't want to break the entire image into all parts. We want only parts of interest, such as tumors and so on. But anyway, the general theory says, let R represent the region of the entire image, the space of the entire image. Segmentation may be viewed as breaking that region into n subregions, R1, R2, Rn, so on, such that these are the conditions. The union of all these Ri's should be equal to R. That is, all of these regions put together must give you the total image. That is, every pixel in the original image must belong to some region. You can't throw away some pixels. Ri is a connected region. Each region has pixels that are connected spatially. But one region here, another region there could belong to the same object, like calcification. That's a different story. Ri, the intersection with Rj, or the superposition of two regions, must be 0. That is, two regions should not have anything in common. A pixel cannot belong to two regions. The regions are disjoint. They're adjacent, they could be adjacent, but no pixel belongs to two regions. There is some predicate P, some property P of Ri that must be true for each region. So each region has a certain property or predicate that is true, but if you apply that rule to the union of two regions, it should be false. That is, if I take two regions and put them together, that test must fail. That doesn't apply in the case of mammograms again, because we say calcifications, there are multiple calcifications. This calcification, that calcification will have the same property. So that doesn't apply. Yeah, the intensities of the pixels in different regions are different, but in mammograms that's not applicable. So these are general conditions in general image processing. So seed-based region processing, we have seen this for adaptive neighborhood image processing. So I won't go through this. It's the same thing. Splitting and merging, I already mentioned that, so we'll skip that. region growing with additive tolerance, that is also what we already talked about. Okay, let's talk about this in a little bit more detail. One of my students, Liang Shen, explored region growing for adaptive neighborhood image processing in a little bit more detail, and we have modified it for different applications. So one of the methods for region growing is to say, compare FMN with the seed and ask what is the difference. Earlier I said for mammogram contrast enhancement, we took FMN minus seed divided by seed. We took contrast. Here it is just the difference. This is called additive, or just the difference. The question is, do you always want to compare with the seed pixel when you are growing a region? The seed could be here and you are checking the neighbors and you are growing, and you are so far away from the seed. Do you still want to compare with that seed from where you started? Or would you rather compare with something around where you are sitting at this present stage of region growing? You saw that mountain with the snow and the seed was there, the region kept growing. And why do you want to compare this pixel with the seed that is so far away? So that is one question. So Liang showed this example. This is a made-up example. Some image that is supposed to be the object. So these values are similar. You can see 127, 126, 124, 5, 124, 25, 26, 27, 28. Compared to 100, 101, 2, and so on. So yeah, there is difference, okay? But if you start from this and do region growing using that technique, that with t equal to 3, you get that, which is okay. But if you start with this, you get this region. This fails because 128 minus 124 is 4 and the threshold is 3. So this is still a pixel within that region. We don't want such differences. So for this, we said use the running mean of the region as a reference, not one seed pixel. Although we start from there, once you include one pixel, the reference becomes, what is this value, 127. You include this pixel, the reference becomes not 127 but 126.5, the mean of the two. And then you include that, it becomes the average of those three. Include this, it becomes the average of those four. So this we call a running mean. Every time you include a pixel in the region, you compute the average of all the pixels in the region being grown. And that is a running reference. Running meaning it is changing every time a pixel is added. And then in another application of fuzzy region growing, we said we will include a pixel if it meets that condition, but we also maintain variance and check the variance. If the variance is disturbed substantially, then we don't include that. So you can put more and more statistical conditions and maintain a reference that is not just one value. So if you do that, this is region growing with a running mean and also the current seed pixel which will come next. Then we get the same result no matter which of these pixels you use as seed. And then there is the, this is what I said. FMN minus mu RC is the reference, less than the threshold. Mu RC is just the average of all pixels belonging to the region. So then he also suggested the use of the current center pixel as the reference instead of the seed pixel. I think I have a picture here. Yeah. So that is a seed, and these are the shaded pixels are pixels included in the region, the others are not in the region. So suppose you are doing that and you are coming here and you are checking this pixel, these neighbors for inclusion in the region. So the center of this block is here, And instead of comparing these pixels with that, you say we compare here. That is another possibility. Ni minus C must be less than a threshold. So this is another possible criterion. Which one works for you depends upon your image, whatever variations exist in the kind of images you deal with. But these are a few different possibilities as to how the reference may be computed for region growing. The idea is that given a region, using any of the pixels within the region as a seed should give you the same result. And that was achieved here. That was not achieved when just a seed was used. That seed gave this result, this seed gave that result. The previous method said you're comparing just the difference between two pixel values, two values. And this one says, take a reference. What should be the reference? Fmn minus mu divided by mu. The mean of the region is used as a reference to compare an incoming pixel. Fmn is a new pixel being considered for inclusion. So compare it with the mean and take a ratio. And that must be less than some tau. It's like a contrast. Or you can use the other f minus b over f plus b formulation. And we put 2 there to normalize, to say this, it is the average of these two. These two divided by 2, so it goes there. So you can use different definitions. We call this multiplicative tolerance because this difference is compared with the product of tau with this average value. So additive, multiplicative, contrast, and simple difference. I'll skip this, but essentially what was done here is how is region growing affected by noise, the presence of noise. But I think I'll skip that, that's not very important. Liang Shen also proposed iterative region growing. That is, the multiplicative tolerance tau that is used, depending on the value of tau used, you get different regions. We don't know in practical cases what that tau value should be. To grow regions corresponding to microcalcifications, we found that using one parameter is not adequate. We may get one region, but we're not sure if that is good. So we said we will grow multiple regions with multiple threshold values, and then among them we will select one that appears to be stable. We don't know which one, we get a whole range of these regions. As you increase the tolerance, the region gets bigger and bigger and bigger. You allow more variation. And we feel, we thought our plan, our idea was that as this region grows larger and larger with more tolerance, there is a stage where the change from one level to another will become small, and then suddenly when the tolerance is too big, the region becomes excessive. It just, we say, explode to something very large. And that's when we say we will cut among these regions. So we characterize these regions with increasing tolerance levels obtained using a certain step size. It could be expected that the values of the feature set at successive tolerance levels will be either the same or similar. How do you compare these regions? We compute some parameters, shape parameters, size parameters, or area, and so on. If the area suddenly changes, then that's not good. So we compute a feature vector. K1, K2, K3, and so on. And we compare the feature vector instead of the actual regions. So this is simply taking the difference between the feature vector at the kth iteration compared with the k plus 1th iteration. How much did the features change coming to the current step compared to the previous step, normalized by this factor, sum over all of the M features. And that is the difference, normalized difference. Find the minimum of that change over all K, the multiple regions you obtained for different tolerance levels, and take that one. So that is considered to be the most stable region among the various regions obtained. I'll skip that. So here is an example with some synthetic cases. So there is a small dark region, and there is this partially occluded circle. There is a circle here that is occluded by the square and none of the circle. So these two regions have been grown properly. There are different levels of noise added, and if you use the fixed methods, you get poor regions. This is not detected. This is not detected properly. The black region and the white region at different levels of noise and contrast, they're all detected properly with the final method I showed, and not the others. If there is no noise, there is no problem. But in the presence of noise of different levels, the details are there, then we get good results here. H is let me see, GH, regions grown with the iterative algorithm with adaptive tau. So by creating these examples and adding noise, we can study the effect of region growing in the presence of noise as to where it fails. It is failing here, we're not getting the whole region. Without noise, there is no problem. With noise, one of them will fail. I get this, but I don't get that. Here also, it's good segmentation here, but not there. Here, both are segmented properly. The black triangle and the partial circle there.